Hey everyone, Professor Hank here. So today we're going to talk about the theory behind the pointer-based queue. And the queue is a first in, first out data structure, and you can think of it as an abstraction of, say, a line. Think about a line at a grocery store or at a bank or something like that. The first person that goes into the line is the first person who's going to be served or is going to be coming out of the line. And so when you have a pointer based list like this is basically a variation of a linked list. You're going to have something that's going to represent your node. You can have something that's going to have a next pointer in it and something that's going to have some variable to store whatever it is that you are going to be storing in this data structure. So for this discussion, let's say that we're going to be creating a queue that stores characters, for example. So we're going to need to keep track of a couple of things. We're going to need to keep track of the front of our queue and the back of our queue. Let us say that we've got pointer or a reference, and that is going to store the memory address of the first item in our queue. So if we've got a node that is storing, say, the character A, then that front reference is going to be storing the memory address of that first node. And so that represents the front of our queue. Okay, now we might have more than one item in our queue. And so if that's the case, then we might have a picture that looks something like this. Now we've got our front reference, but we're also going to keep track of the back. So we're going to have another reference, another variable that we'll use to keep track of where the end of our queue is. And the reason we're going to do this is because it's going to speed things up. Okay. So we have generally two scenarios that we have to deal with. We're going to have to deal with a empty queue and a non-empty queue. So for an empty queue, we're going to have a picture that looks kind of something like this. If we're going to have two references, then when there's nothing in our queue, then we got our front reference and our back reference, and they both have to point to null. Okay, because there's nothing in our queue. But that's our first scenario. Our second scenario is something like this, where we have a non-empty queue. Okay, so we're going to look at both of those and how we can interact with this data structure. So we will look at algorithms for adding something to the queue, also known as the Enqueue operation, taking something from the queue or removing something from the queue, which is also known as doing a dequeue. And then we'll also add an algorithm for, peeking and taking a look at what's at the front of the queue. We'll start off by examining the Enqueue operation. Okay, so to do an Enqueue operation, to add something to our queue, we're going to need to have access to that front reference. We're going to need to have access to that back reference. And then we're also going to need to have the value that we want to add to our queue. So if we have an empty queue, again, remember, it's going to look something like this, right? We've got the front and the back both set to null. So that's a definition, right? Our queue is empty when this scenario exists. So now when we want to add something to our queue, then the first thing we're going to have to do is we're going to have to create a new node. We'll do that using dynamic memory allocation, and we'll take the memory address of that new node and we'll put it into some temporary variable. We'll call that n. Then we're going to assign to our new node the value that we want to store. So let's say that the character variable is named I. You can create your node, using a struct or a class, whatever you want to do, but we're going to have to assign to it the next value. And so when you do an Enqueue operation, the new node is always going to go at the end of your list. Okay, so that means that the next pointer in your node should always be set to null. So we're going to assign to that next pointer in our new node null. Okay, now remember, we've got two different possibilities here. We've got an empty list, but we also have the scenario where we have a non-empty list. So we're going to have to take both of those in account, and we're going to have to make sure that our algorithm handles both of those scenarios. Okay, so first things first, we'll go ahead and deal with the empty queue first. So how can we tell if our queue is empty? Both the front and back pointers or variables are set to null. So we could just do something like this. We can say, well, if the front is equal to null, then let's do something. Okay, now you could just as easily have checked back because in this case, they're both set to null, but I'm just going to go with front because I want to. Now, if that's the case, then what are we going to do? We're going to set both front to our new node and back to our new node, right? So we're going to assign that front variable and that back variable the contents of our temporary end variable, okay? Now, let's trace through the code and make sure that it handles our first scenario. All right, so what do? We enqueue. So let's say that we are invoking a function that does an enqueue or a method on a class. Okay, we would need to have, again, access to the front pointer and make sure that it's updatable because we're going to be changing the contents. We have to have access to that back pointer or variable or reference, and it has to be updatable. So if this was a standalone function, you'd be using pass by reference, for example. If it's in C++, if it's a class attribute, then it's just you have to make sure that it's in scope. Is basically the big idea here. And we also have to have the value that we want to assign. So let's say that the value we want to assign is A, because for this discussion, we're storing characters. Okay, so let's look at our algorithm. First things first, we get a temporary variable called n. We create our new node. We assign its address to n. And then that's the first step. Second step is we assign our value to the character variable in our node. So in this case, it's A. And then we set the next to null. Okay, fantastic. Now we check to see if the queue is empty. So if the front is set to null, in this scenario 1 it is, then what do? We update front and back. So we're going to overwrite the contents of that front variable with the contents of n. So now it's pointing to the node. And then we update the contents of the back variable with the contents of n. So now it is pointing to our new node as well. Now, once the algorithm's done, this temporary variable can go away. Okay, and so what are we left with? We're left with a queue that has exactly one thing in it. We've got one node in it. We've got the front pointer and the back pointer, the front variable and the back variable, both referring to the same node, which makes total sense. Since there's only one node in our queue, then we're going to have that node be both the front of the queue and the back of the queue at the exact same time. Now, the other scenario we have is what happens if we have a non-empty queue, scenario 2. Well, remember that in that case, whenever you're doing an enqueue, you're going to be putting your new node at the very end because the new person coming along for the line, they have to go at the end of the line, right? So what are we going to do? Well, we're checking to see if the queue is empty. It's not in this scenario. So we'll come down and we'll have a little else going on. Okay, now what do we do now? Well, the nice thing about using this back pointer is that we don't have to traverse to the end of the list like you would in a regular old linked list, which is a big O of n operation. We don't want to do that. That's inefficient. So instead, we're going to leverage this back pointer. So we're going to pay a little bit in terms of memory to gain a much more efficient runtime. So that way, instead of having a big O of n, what we're going to end up with is a big O of 1 or a constant time operation. So what do we have to do? Well, let's go through our algorithm. So we create the new node. Step 1, new node's created. Step 2, we assign the value. So let's say that we had in this scenario something like this, right? We're calling our algorithm. We're giving it access to front and back, and the value that we're going to assigned to the node is that we want to put into our queue is like G. Okay, so we create our node, we assign to the variable that's storing the value, so G. And then since this is going to go at the end, we're going to set its next to null. Now we check to see if the list is empty. If front is equal to null, it's not, because it's got the memory address of that first node, right? So it's a non-empty queue. So we skip all of this stuff. And so then we kick down to our else. So what do we need to do? What we need to do is we need to attach this new node at the very, very end. So we'll go ahead and set the back node's next pointer to our new node, right? And remember that our new node has its address in that temporary variable, that n variable, right? That we create right here in step 1. So what we'll do is we will set the node whose address is in B, we'll take its next pointer and we'll overwrite the null that's in there with the memory address in that n variable, which is the memory address of our new node. So when we do that, it's no longer pointing to null, it's pointing to our new node, which is what we want. Now we're not quite done yet, because we always have to have that back variable, that back pointer, that back reference referring to the last node in the list. So we have to do one more step. We have to update the B variable to what? Well, we have a couple of options here. We need to have it storing the memory address of this node right here. Now, where can we access that memory address? Well, it's stored in one of two places, so we could pick either one. Its memory address is either in the temporary n variable, or it's now in the formerly last node, its next variable, right? So you can pick whichever one you want. For consistency, maybe, I'll just set it to n here as well. Maybe it looks a little bit neater to do that. So then when we do that, when that step executes, B set to n, then we overwrite the contents of B with the contents of n. So then our back variable is now pointing to our new last node. And so that's it. Okay, so that's how it works. Now, one thing we could do is one more test. You always want to think about, particular edge cases or something like that. What happens if we were to have a queue that only has one node in it? Would our algorithm still hold up? Well, let's take a look, right? So in a one node queue, both front and back are pointing to the single node. Now let's say that we wanted to do an enqueue here. So let's say we're going to enqueue. We need to have our front and back in scope. Let's say that we're going to put in, I don't know, X. Doesn't matter for this example. So let's follow our algorithm. What's the first thing that happens? We create our new node. We have a temporary variable that's storing the memory address of that new node. Then we're going to assign to our new node the value that we want to store in the queue. So in this case, G. And then we set that new node's next to null. Now we check to see if the list is empty, right? We check to see if the queue is empty, if front is equal to null. Well, it's not, because it's got the memory address of the one node in the list. So we skip that block and we go down to our else. So what do? We set B next to n. So what's B next? B next is right there. So we set that to n. So we take the contents of that n variable and overwrite the null inside of our node. And then we set B to n. So we overwrite the contents of B with the contents of n, and we've got our list as we need it. And so once the algorithm's done, this local temporary variable goes away, and we now have a two-node queue that's got the front pointer, or the front variable, pointing at the right place, and the back variable pointing to the right place. And the value is stored in the correct position at the very end. So that is your Enqueue algorithm, and this thing is going to execute in big O of 1, because the number of operations that you have to execute in order to add a node to your list is not going to change based on the length of the list, right? There's no traversal that happens here. So it's going to be a fixed number of operations no matter how many nodes you have in your list. Okay, so now let's look at the Dequeue algorithm, and it's basically pop for a pointer-based stack, more or less. So let's take a look at it. What are we going to need? We're going to need front, that front variable. We're going to need that back variable in scope, And that is it, because we're not adding anything to our queue. We're taking something out. So what are our potential scenarios that we're going to talk about? We're going to have to deal with a empty queue. We have a one node queue. So we'll make sure that we handle that correctly. So we got our back variable and we've got our front variable. And then we have, a multi-node queue. We're going to make sure that we handle that correctly. So, if there's 2, 3, 4, 5, 20,000 nodes in the queue, we want to make sure that we handle that correctly as well. So first things first, first scenario, right? Remember what Dequeue is doing. It's just taking what's off of the front of the queue out. We're just going to remove that. That person that's at the front of the line, they're being helped. They're not going to be in the line anymore. So first things first, there's nobody to remove from a line if there's nobody in the line. So we should check to make sure that there's actually somebody in the queue. So the only time we're going to do something is if the queue is not empty. So we can do something like, if front is not equal to null, or if back is not equal to null, then we will do something. So I'll be consistent with the Enqueue operation, and I'll just stick by checking the front variable. Now you could check either one, because remember, empty queue, front, back, both set to null. So we're only going to do something if our queue is not empty. So that handles this scenario right here. Now, if it's not empty, then what do we need to do? What do we need to do? So let's look at scenario 3 here. What we need to do is we need to remove that first node. Remove the first node and update the pointers to make sure that we don't break our list, right? So we have to do those two things. So we have to make sure we don't have a memory leak. So in C++, we'd have to delete our node. If you're doing something with automatic garbage collection, they don't necessarily have to worry about that step, but we're going to assume for this example, C++. Okay, so what do we do? What do we do? What do we do? We're going to need to hold on to the memory address of that first node. Okay, so we'll do something like this. We'll say P is set to N. So P set to F, right? Because F has got the memory address of the first node. So we'll do that. And then what we'll do is we'll advance that front variable, that front pointer. Okay, so we'll go F to F next. So when we do that, we're overwriting the contents of our front variable, our front pointer, with the contents of the front node's next pointer, which has the memory address of the following node, right? So we get a picture that looks like this, okay, which is exactly what we want. And then from there, we're free to delete our node, right? So we can do something like this. We can say delete P. Okay, and when we do that, then that first node leaves memory and we're good to go, right? And the P variable is a temporary local variable, so it leaves as well. No memory leak. The first node has been removed from the queue and all of our pointers are in good shape. Our variables are in good shape, the front and back. Now, let's check scenario 2, and you're going to see that there's a problem with this, and we're going to have to deal with it. So let's go through and do a dequeue on our one node queue. So if front is not null, that's true because front's pointing to this node right here. So let's do our temporary variable P, which is going to be assigned the memory address of that first node. And then we'll advance our front pointer, our front variable, to F next. So we're going to overwrite the contents of F with F next. Now what's F next? F next is pointing to null, right? So now let's delete P, which means we're going to delete the node. Now, maybe you see a problem here. Well, as soon as we delete the node, what's our back variable? What's our back pointer pointing at? Invalid memory location, right? It's left referring to a node that no longer exists. So what do we have to do? We have to check for this scenario and fix it. So how are we going to do that? Well, is there a particular state or is there a particular content of the front variable that could help us out? Yeah. See, now the front variable in this scenario has contained null in it. So all we have to do is check to see if the front variable is pointing to null. If it is, that means we have an empty list again. And so we got to update our back to also point at null, because remember, the definition of an empty queue is when front and back are both referring to null. So if front is null, then back needs to be null as well. And so this if will kick in. It'll evaluate the true in this scenario. We overwrite the contents of B with null, or we could also overwrite it with the contents of F, since F contains null too. I mean, either way would work. But for us, we'll just be consistent and we'll go with the back equals null. And so as soon as we do that, then we end up with front and back both pointing to null and an empty list, as it should be. So this is going to be a big O of 1 operation. Why? Because the number of operations doesn't change based off of the length of the list. So no matter how many nodes there are in the list, you're going to have the same number of operations. So let's say that we've got 10 nodes in the list and we're going to do a Dequeue. Well, we're only ever interacting with that first node, right? So you might have however many nodes here, but what do? You check, is front not equal to null? That's true. So that's one operation. Then you create that temporary pointer or variable P and assign it F. So that's the contents of the F variable. So that's another operation. So that's 2 operations. Then you update your front pointer, your front variable. That's another operation. Then you delete your node. That's another operation. And then you do your test. If front is equal to null, that's another operation. Now, if it was, then you'd have to assign B to null also. So you'd have a total of 6 operations. Does that matter how many nodes there are, right? I mean, it doesn't matter if there was 10 million nodes in here or if there was 6 trillion nodes in here. The number of operations is always going to be 6. So that means that it's a constant time algorithm. And so constant time, another way of writing constant time, is big O of 1. It's very, very efficient. Okay, so let's look at one last algorithm here. We're going to look at the peek algorithm. And peek just allows us to look at the front of the queue without modifying the queue. So what do we have to have in scope to do this? All we need to have access to is that front pointer, that front variable, in order to make this work. So what are our scenarios here that we have to worry about? We have either an empty list, an empty queue, or a non-empty queue. And it doesn't matter how many nodes there are in the non-empty queue, because we're only ever going to be looking at the very first node. First things first. Number 1, if there's nothing in the queue, there's nothing to look at. Right? So the only thing we should do is return a value if there's actually something in the queue to begin with. So we'll do something like this. We'll say, well, if front is not equal to null, then we'll go ahead and return the value in the first node. So return f dot I. Remember, we used I as our variable name for the variable that's storing the value we actually have. So that is our algorithm. So this is going to be big O of 1, because how many operations do you have? No matter how big the list is, you've got an operation right here and you've got an operation right here. There's 2 operations. It doesn't matter how big the list is. You're only ever looking at the first node. Now, let's make sure that this works. We don't have any bugs or anything. We're not accessing any invalid memory locations. So first scenario, empty list. If the front pointer does not equal null, well, this is false. So algorithm's over. So we don't return anything. So check. Now what about the non-empty queue, the non-empty list? If f is not equal to null, if our front variable is not pointing to null, well, that is true in this case. So since that's true, let's say that, I don't know, the value in here is L. So what we're going to do, we're going to return f.I which is the first nodes, the front nodes, contents of its I variable, and so we end up returning L. So it works in both scenarios, so we're good there. Okay, so that's all there is to it. Now you know the basics behind how to implement a pointer-based queue in the language of your choice. Thanks for watching, and we'll see you next time.